Now that we've introduced the central or the confidence interval and the idea behind it, let's go ahead and do one confidence interval here. So the first thing that we're going to do is I'm going to look at the confidence interval that I want. So I'm going to draw my normal distribution. My mean 0 is right here, and I'm going to look for this negative and positive z-scores. I'm going to put these in blue because that's what I'm trying to find, right, is that blue score that I drew on my last page, and I'm going to be doing that based upon the confidence level. The confidence level is the area in here. So 0.9 is equivalent to 90%, so this is 0.9. So remember what that means is that 1 minus alpha is equal to 0.9. So that means that alpha must be equal to 1 minus 0.9 or 0.1. And it's not really alpha I'm interested in because remember alpha is in here and in here because this is 1 minus alpha, right? And if I'm interested in looking up to get this z, then I need to know how much is just in this tail down here, and that would be alpha over 2. So I'm looking up 0.1 divided by 2, and so that's going to give me 0.05. And so it is 0.05 that I'm interested in. So I'm going to shade this in here, and I'm going to shade this in here, and I'm going to remind us that we have 0.05 in both of these tails. So 0.05 in both tails, and that means that this is what I'm looking up, right? The probability that a z is less than that z that I'm looking for is equal to 0.05. And that z that I'm looking for, I'm going to represent with a blue marker because that's what we were used to. So we have a negative z-score. Now when I find this, of course, this z is going to be plus or minus that value because this and this z, the left one and the right one, are exactly the same. They're just opposite signs. So I'm going to go over to my z table and I'm going to take a look at that. So in my z here, I'm going to go and I'm going to find as close as possible to 0.505. So I have 0.050 here, and I have 0.0495 here. Now you'll notice in this table, right smack dab in between those, there's a star. And that's because this is such a commonly used value. And that star represents 0.05 exactly. And if you scroll down here, you'll see that they've already done the averaging for us. That's negative 1.645. And that is the value that we're going to use for a 90% confidence level. Our z-score, our critical value, remember this is called a critical value, is going to be 1.645. I don't want us to round this one to 2 digits. I want us to use this one as a 3 decimal number. So this is our critical value. So that's how we find our critical values. Now remember, if we were going to do this on our calculator, we would do inverse, normal, and that would come from the distributions menu, remember, and then we would put the area to the left of the value that we want, 0.05, and on the old operating system that's all we'd need. The new one, it already has a 0 and a 1, so it'll place it in there for us, and then we would return, and we'll come up with 1.644853626, which rounds to exactly the same number as we see here. So either way we look at it, we've got that value. All right, now let's take a look at the next example here. Okay, so these basically are the critical values that we find in the table, and I showed you that, and we also do it on our calculator. Now there's another table that I'd like to show you, and let me see. I'm going to pause this for a second because I'm not sure if I have one on the computer. I may have to get one. Okay, yes, I do have a t-table, and this in the Brace book is on appendix 2 on A24. Now, the t-table is for the t-distribution, which is associated with the normal distribution. And a t-distribution, when we have something called degrees of freedom that are really, really large, and some books will call it infinite degrees of freedom, and some will call it just large degrees of freedom. I think the table that I'm referring to here in my note, or on the computer, has infinite, if I remember right. But at the infinite, this distribution, this t-distribution, becomes approximately normally distributed. So if we use the t-distribution, or the t-table, at a degrees of freedom where we have an infinite or large, then we're actually looking at the same values as for a normally distributed random variable. And the t-table is really super easy to read, so let me show you that on the t-table. So here's what a t-table looks like. Here on the left side of the t-table you'll see degrees of freedom. Now up at the top of a t-table you have areas for one tail, you have areas for two tail, and in the Brace book they give you confidence levels. Well, that's kind of cheating because most tables do not have the confidence levels there, so don't get used to seeing that. Get more used to seeing what you see right here. So what we have is the area in one tail, which is the 0.05, is right here, and you'll notice that the areas in two tails is equal to alpha. So one of the things that you could say here is you could say that this thing is equal to alpha. So this area in two tails right here, that's equal to alpha. So let me type that in, is equal to alpha. And alpha, remember, is that kind of fishy looking thing. And then in this one here, let me add another sticky note here. This one up here, this one is equal to alpha divided by, oops, it's not going to like that, divided by 2. And so one tail is alpha divided by 2, and two tails is equal to alpha. So what we have here, oops, see, it didn't like what I did. So alpha over 2 is 0.05 and alpha is 0.1, and that's what we had here, right? Those two numbers right there. Now I'm going to scroll down because in the t-table, like I said, it has these things called degrees of freedom. And when the degrees of freedom is large or infinite, that's the value that we have for our z's. So this value right here at the bottom, you see where my cursor is here, that value is the same value that we came up with, and that's always going to be the case. Whatever you see down here at in this large value, those are z-scores. So the t-table is awesome for finding critical values. It's kind of made to do that. So anyway, that's why I wanted to show you the t-table, and we'll use the t-distribution later, so you've kind of been introduced to it, so it makes it very nice to use later. All right, now moving on. So this explanation here is what I gave you at the very beginning of our lecture in introducing a confidence interval to show you how we were going to get these confidence intervals. So this introduced what we call the margin of error. And the margin of error is denoted with an E. So what we have, and let me write this out, is that we have this E, which is the margin of error, being equal to all of this part right over here. And that margin of error is the z alpha over 2 value, and that is just the critical value. Okay, so this is our critical value, we'll call it a CV, okay, times sigma divided by the square root of n. And so that thing is called the margin of error. And all we do to get this margin of error is it comes from basically solving this interval that we started with backward so that we get mu, because what we want to do is we want to come up with an interval that puts mu in the middle, the true population mean, between a negative value and a positive value with this amount of probability, that confidence level's probability. So this margin of error comes from our critical values. And then because this interval is based upon the point estimate, then we're going to add or subtract that margin of error to our point estimate. So our point estimate. And our point estimate for a normally distributed random variable where we're trying to estimate the mean is x bar. So x bar plus or minus our e is going to be a confidence interval with 1 minus alpha % confidence. And that is going to be our interval. So we're going to use those critical values the way that we just described. Now when we're finding a confidence interval, when sigma is known for estimating the true population mean using the point estimate x bar, we must have all of the circumstances met so that we can use the central limit theorem. So we must know that our values come from an approximately normally distributed random variable, or we must know that the sample size is over 30. The standard deviation of the population has to be known. Now, that really doesn't happen very often in the real world, and we'll find out later what happens when it isn't actually known. And then we also must find the critical values, and then we're going to compute our interval based upon those critical values. So let's do one really quickly here. So if we have a sample of size n equals 20 from a normally distributed population with a variance of 225, so sigma squared is 225, which means that sigma is equal to the square root of that, which is 15, and a sample mean, which is equal to 64.3, we want a 95% confidence interval for that true population mean. So for mu, so we're going to find mu, an interval which mu could possibly be in, for a sample of size 20 with this sample mean when we know the population standard deviation. Now because it's approximately normally distributed, we don't have to worry that this is less than 20. Or less than 30, sorry. So what we want to find is we want to find what puts 0.95 here in terms of a negative z over here and a positive z over here. So what we need is alpha over 2, which is equal to 0.05, right? That's alpha, 1 minus 95 divided by 2, which that is a 0.025. And so what I'm looking at first of all is my critical value, and this is my critical value, right? And what that is the probability that a z less than that negative z is going to be equal to 0.025. So I'm going to go over to my t-table, and I'm going to look that up. So my t-table, 0.025 in one tail or 0.05 in the other tail, I'm going to scroll down to the bottom where it's large, right? And I'm going to find that's 1.960. So this value here is 1.960. And it's a minus over here and it's a plus 1.960 over there. So those are the values that I'm going to use. Now with that critical value, I'm going to find my margin of error E. So my margin of error E looks like 1.96 times the standard deviation of the population, and then divided by the square root of the sample size. And so I'm going to compute that margin of error really quickly. And I get approximately 6.574039. So I'm going to have x bar plus or minus that e. And we'll compute an interval that goes from a low value to a high value. And I'll finish that next time.